Thank you. So thank you, Sergey. Slideshow from the beginning. Thank you for the nice introduction and for inviting me to this nice conference. I will talk about small angle neutron scattering on semi-crystalline polymers. I am Aurel Radulescu, coming from, or I'm speaking from Garching. So hello everyone from Garching. So what is the why? Okay, so next slide. So semi-crystalline polymers, as we all know, they are showing good thermoplastic and elastomeric properties. They show good strength and wear and good chemical resistance, and they are characterized by two temperatures, melting temperature and glass transition temperature. So they are composed of crystalline and amorphous regions, and they are used in a very large variety of applications, from everyday commodities up to special fields like aerospace or fuel cells. And in order to learn about these materials, first of all, we should know their microstructure, and they are characterized usually by a hierarchical organization of different structures and morphologies. And they are characterized by different size levels spread over a very broad scale lengths between angstrom and micrometer range. And small angle neutron scattering and small angle X-ray scattering combined with ultra small angle and wide angle scattering experiments are the typical methods used for characterization of structure of such materials. Of course, the dream is to have all these options, the very broad Q range or a very broad length of scales, covered at the same instrument, and I can say that the dream comes true. Some instruments can already provide this opportunity. So now I'll start with a few applications. So crude oils and middle distillates, when the temperature approaches 0 centigrade or drops below this temperature, these materials are showing a degradation of the viscoelastic properties, and motors, diesel motors are stopped, so the filters are clogged, the pipes are clogged. You can see here what happens in these conditions. And this is because phase separation of paraffins or waxes of long chain alkanes appear at this temperature, and you can see here chromatography description of diesel and crude oil systems. And the waxes are forming so-called house of cards morphology of hundreds of micrometer large and very, very sharp wax crystals. And that's why additives are added. These are nothing else than semi-crystalline polymers in order to modify the morphology and to improve the viscoelastic properties of such materials. And you can see here what's the difference between untreated and treated diesel and model crude oil system. Now, another example is from the polymer membranes used for energy applications. So fuel cells, we have proton exchange membrane and anion exchange membrane fuel cells, depending on the species, which are conducted between the electrodes. And the exchange membranes are also semi-crystalline polymers. Now, proton exchange membranes are showing a high ion conductivity, excellent ionic properties in solution. However, they work in acidic medium, so we need noble metals for electrodes, platinum usually. And that's why proton exchange membrane fuel cells are in limited use for the moment. So these are the only fuel cells in use, but nevertheless, the use is limited. And there is no possibility for a large-scale commercialization because of the high price. And there are also some issues with the Nafion, which is the benchmark for these applications regarding the exchange membrane. Now, anion exchange membranes show they are a good alternative, show some advantages. They are platinum-free systems. They operate at low temperature. They don't work in acidic medium. But they are still showing low ion conductivity, low thermostability, and low durability. That's why this is a promising alternative, but not yet mature for such applications. And there is an intensive work spent to improve these systems and to find new membranes which are approaching properties of Nafion, but are better and cheaper regarding the price. Now, Nafion is the benchmark in fuel cell industry. We can see it's characterized by nice conductivity, conductive properties. However, so efforts, as I mentioned, efforts are spent to find alternative materials, and any such material, new material, should fulfill the condition that it shows a microscale phase separation regarding the structural characterization and in hydrophilic conductive domains and hydrophobic crystalline regions. This is the optimal combination to provide high ionic conductivity and good chemical and mechanical stability. So, however, in order to decide about new materials, we should learn about their microstructure, and we can see here there are only a few examples from a multitude of such proposed morphologies. Even for Nafion, the nanomorphology is still under investigation. It is not yet clear how this material looks like at the microscale. Now, another material is the semiotactic polystyrene. This was discovered relatively recently, end of the 80s. And this semi-crystalline material shows two very interesting properties. First, it can form co-crystalline structures with small organic molecules, which can be hosted at guests in the spherical or cylindrical cavities between the helical conformation of the polystyrene chains. These are the so-called delta and epsilon flat rates. And in the same time, this material shows a very rich variety of crystalline forms. So the alpha and beta forms are characterized by polymer coil in planar zigzag conformation, while epsilon, delta, and gamma forms are characterized by helical conformation, trans-gauche conformation of the polymer chain in crystalline form. So these properties are very important because, first of all, we can load this material with active guests so that we can obtain advanced optical materials, chromophore, fluorescent, photoresist, reactive. We can obtain ferroelectric and paramagnetic materials. Then this material can be useful for lithium-ion batteries when it's combined with ionic liquids. And also very important is the selective functionalization of this material in delta and beta form when we can sulfonate only the groups in the amorphous regions, amorphous phase of the material, keeping the crystalline form conserved. And what is this? It's going. Okay, so to characterize such complex morphologies, we can call them multi-component systems, because when we hydrate or we load the semiotactic polystyrene with guest molecules, we have several components in our sample. So we use a small angle neutron scattering technique. So it was introduced this morning by Laszlo Almasi. So we come with an incoming beam on our sample. Then the scattered neutrons, we consider the scattering as being elastical, and the scattered neutrons are recorded on two-dimensional detector at different scattering angles, and we analyze the data as a function of wave vector transfer. We work in a reciprocal space, and then we can do the radial averaging over the entire detector or over selected sectors, and we get our scattering curve, which is interpreted via models to get the structure, morphology, size, orientation, shape of the scattering objects. So the scattering intensity is characterized by the contrast factor squared, which is the difference in scattering length density between the object of interest and the environment in our sample, by the form factor, which is the characteristic of intraparticle correlation, so gives delivers information about size, shape of scattering objects, and the structure factor interparticle, which characterize the interparticle correlations between scattering objects. Now, very important is the contrast factor, which is the difference in the scattering length density between different components of a complex system. And for hydrocarbon materials, very important is the fact that the neutrons are seeing differently the hydrogen isotope, so the protium and the deuterium. So the The coherent scattering length is significantly different between these two isotopes, and this gives us the possibility to do selective deuteration of parts of our complex sample in the chemistry lab without disturbing the sample properties, so that we can make parts of the sample invisible in our neutron scattering experiment. An example is here, core shell morphology in water, working with deuteration, protonation of water. We can see either the core or the shell, or we can see both of them. Now, this technique is applied at reactors or spallation sources working with continuous beam or with chopped beam, with a pulsed beam. So you can see SANS diffractometers at the nuclear reactor. So they use the pinhole geometry. They are typically very long instruments because we have to move the detector at different distances in order to be able to detect scattered neutrons over a very broad angular range for wide angle up to very small angles, while at spallation source working with a broad wavelength bands and with a multitude of detectors in fixed position. The neutrons are recorded on the detector based on their flight time, so they work with pulsed beams. So the choppers are giving the 0 time, and then the neutrons are flying, arriving on the detector, and they are recorded based on their flight time. Now the data interpretation can be done very quickly, observing different scattering features like plateaus, power laws or transition points, or can be done in terms of models, structural models, either analytical or numerical. The idea is to obtain information about size, orientation, and shape of the scattering objects. Now I will skip these two transparencies. So first, what about diesel and crude oils? So polyethylene, polyethylene propylene diblock copolymers are usually good additives for such systems, what I presented you in the very beginning. So these are diblock copolymers, crystalline polyethylene, amorphous polyethylene propylene in hydrocarbon solvents. And the morphology of aggregates formed by this material is done by the balance of entropic forces resulting from the stretching of the amorphous block and the enthalpy contribution from the folding of the crystalline block. And we are dealing with a ternary system, core, brush, and solvent. We have here the description of the form factor, the contrast factor, and here are a few examples obtained for a low molecular weight material, so short blocks in either core, brush, or common contrast. And by interpreting these scattering curves together for different contrast conditions, we obtain information about size and morphology of size and shape of such a complex morphology. So it's a core, brush, lamellar morphology with crystalline lamellae surrounded on both sides by amorphous brushes. When we work with high molecular weight material, so long polymer chains, so then the plates are very large in the lateral extension, and then the van der Waals attraction starts to play a role, and we are dealing with a stack of crystalline lamellae, so we are getting additionally structure factor peak in our scattering data. And of course, we don't see the lateral size of the plate, so these curves are going up towards lower Q. Now, what happens when we mix this material with paraffin waxes, so long chain alkanes, either C24 or C36 molecules? So we use the same approach, different contrast conditions, and selective deuteration was used to understand what is the crystallization mechanism of waxes and why these polymers are very efficient in controlling the wax crystallization and preventing development of large wax crystals in our system, so that crude oils and diesel fuels are still fluid at low temperature. So, and we were dealing with two mechanisms: co-crystallization of wax with the crystalline block in the core, or with the nucleation of wax on the crystalline core. And this second mechanism was confirmed by our experimental results. So the wax, the polymer is first forming its morphology, and then the wax starts to crystallize on the crystalline core. It's growing in wax crystals, but the brushes are arresting the growth of the large wax crystals. So in this way, sans and contrast variation was able to provide information about this complex system and the mechanism of co-crystallization of such materials. Now we worked further with the random polyethylene butene copolymers. These are polymers with a variable number of ethyl side groups along the main chain, and depending on the number of the ethyl side groups, PEB 11 side groups per 100 backbone carbons, then 7.5 side groups per 100 backbone carbons. So these materials are showing different crystalline behavior, but all of them are assembling in one-dimensional objects. And for highly crystalline material, we observed the modulation of density along the cylinder axis, which is given by this correlation peak, which does not change as a function of polymer concentration. So it is correlation along the polymer object. So when we mix this with paraffin waxes, we observe that both materials are assembling, are co-crystallizing in two-dimensional objects, and also we measured different materials, different concentration, different temperatures, different wax molecules, and the highest efficiency in controlling the wax, the crystallization of waxes was shown when we had matching of polymer and wax crystallization temperatures. In this case, we were dealing with co-crystallization of both species in common structures, while when polymer aggregates first, it's templating the subsequent wax crystallization. And this was nicely proven by extended Q range sans experiments. First, the polymer forms its own one-dimensional with modulation of density structure. Then the wax starts to grow laterally of the crystalline nuclei in so-called shish kebab morphology. We observed this with TM. And the surplus of wax is continues to grow and to fill the spaces between these initially formed lamellae, and gives rise to appearance of large needles at very low temperature. However, these objects are much lower than the wax crystals when the wax is crystallizing alone in the system. And in this way, we succeeded to understand the co-crystallization mechanism of these materials. Now we continued with different other block copolymers or multi-block copolymers. In all cases, the wax was crystallizing in much smaller and much softer morphologies compared to the house of cards morphology, which is typical for wax alone. And the sans contrast variation, sans experiments have been accompanied always by TEM or microscopy observations to see the common morphologies. Now, syntactic polystyrene films. So when we work with cast films, we don't see anything from such complex material, which is additionally sulfonated in the amorphous region. So it's becoming hydrophilic. It absorbs water, increasing the relative humidity on the sample. Water clusters grow, and they form in the end water cylinders, water channels. So in order to understand such a complex morphology, we have to stretch, to deform actually the films in order to separate on the two-dimensional detector scattering contributions from different components at different scattering angles. So in this way, we can play also with the contrast. So we can hydrate the film with deuterated, protonated water or mixtures. So we change the contrast in the amorphous region, or we change the contrast in the crystalline region by loading deuterated or protonated guest molecules. Now, this is an example of how the scattering patterns look like: non-sulfonated, sulfonated, hydrated by dipping in H2O. So this is equilibrated membrane, equilibrated in water at different detection distances. What is very important is that for hydrated membranes, we don't see anymore this interlamellar correlation, which is observed for dry film. And for sulfonated film, so sulfonation is also swelling the interlamellar amorphous layers. So the correlation peak is moving towards smaller scattering angles. So, by hydration, we observe a very different scattering pattern. So not anymore correlation peaks, but a sort of butterfly scattering pattern. I will explain it later. What is important at very high Q, playing with the contrast in the crystalline lamellae, we can observe the 010 crystalline reflections when we load the sample with protonated gas molecules, while when we load with deuterated gas molecules, we don't see anymore these scattering features. I forgot to mention that in order to keep the background low, we always work with deuterated syndiotactic polystyrene film, stretched film. That's why deuterated gas molecules, deuterated polymer matrix, there is no contrast, no 010 reflections visible, and no interlamellar peak visible. So now the conclusion is that combining sans and ones simultaneously, it helps for the assessment of crystallinity preservation during in situ sample treatment, relative humidity and temperature, and about mechanical stability of the membrane. Now here's a sketch what kind of scattering features we can observe when we stretch the film and we hydrate the film. So this is 010 reflection at very wide scattering angles. Then the ionomer peak is the correlation between the ionic groups is moving towards lower Q in increasing the water content of the membrane. And then at intermediate Q, we observe the correlation between the lamellar crystalline lamellae of the polymer in the crystalline region. And we can play with the contrast in all these regions of our sample in order to make one or another of these scattering features visible or invisible. So the ionomer peak, as I mentioned, in increasing the relative humidity, is moving towards lower Q. So the ionic clusters are going apart from each other by being pushed apart from each other by the accumulated water, while the crystalline 010 reflection stays unchanged. So it means that the crystallinity of the membrane is not affected by the hydration when the hydration is kept at moderated level. Also playing with different H2O, T2O combination, we observed that the ionomer peak can be matched for almost 100% T2O. So we don't see anymore the correlations between the ionic groups. And we can model using structural models, the scattering patterns over the equatorial or meridian or any other angular sector of this complex two-dimensional scattering pattern, and obtain information about sizes, about densities, and so on. So what happens when we increase the hydration of the membrane? So first, up to 80%, we still see this interlamellar peak in this experiment. The membrane was placed in beam with the stretching axis horizontal. That's why the interlamellar peak is seen on equatorial sector this time. Increasing further the relative humidity, the peak splits into 4 peaks, and then we are seeing at very high humidity this butterfly-like or 4 points scattering pattern, which is typical for crystalline morphologies under deformed state. So these were studied by Hashimoto's group early in 80s, and you can see that tilting the lamellar stacks, we can obtain this 4 points scattering pattern. And this is what happens when we load our membrane with very high amount of water. So water clusters are growing and are forming lately channels, and the channels start to forming the crystalline morphology. While drying further on the sample, we recover the initial scattering pattern. So it means that the crystalline, the lamellar stacks are recovering their initial position. And this is another information about the robustness of these membranes and the preservation of their crystallinity and the mechanical stability during hydration and exposure to temperature. So the water channels have been observed by TEM. Now another, so do I still have, okay, 5 minutes. So I will hurry up. So contrast variation sans with partial scattering function analysis on Nafion, Nafion membranes. So this is also a ternary system. We have crystalline main chain. We have amorphous hydrophile lateral groups, and we have water. And this is an example of scattering results collected for different contrast conditions, so varying the H2O ratio between 0 and 100% in hydration water. And you can see that different scattering features are matched, are getting invisible for some particular values of D2O in our hydration water. So now the typical approach for such studies is to analyze the scattering intensity, but in this case of ternary system contains scattering contribution from all components, main chain, side chain, and water. So the intensity profile is giving only qualitative information, no quantitative structural information of each component. It's delivered by analyzing only one curve. And that's why for Nafion, different models have been proposed along the time, only based on the analysis of individual scattering curves. So recently, the cryo-TEM provided information about a sort of bicontinuous morphology of Nafion. And we apply this partial scattering function analysis. So we have the scattering equation for a ternary system. So we have the self-scattering terms and the cross-scattering terms. Under incompressibility assumption, we get finally only 3 terms with the contrast between these terms, only self terms, while the cross terms can be obtained by combination of self terms. And we resolve this equation, intensities, contrast matrix, and vector of partial scattering self-terms, functions for self-terms, and resolving this equation and evaluating the consistency between the reconstructed SANS profiles and the experimental ones via Beck's substitution, we could obtain the self-terms for each of the 3 components in this system, knowing the scattering length densities and also the composition of the material. So now these are the self-terms of Nafion. These are the intermediate terms. So self-terms, they show some scattering features. It is a sort of bicontinuous features which have been interpreted using Teuber-Streu model. So the Bush was used for low Q. And we succeeded to characterize all these 3 scattering self-terms, and cross terms show a negative sign for main chain. The negative sign indicates a repulsive interaction, while attractive is a positive sign. So this offers information about strong attractive interaction between the side chain and water. So now I will skip the next. So I still have 1 minute or 2, yeah?
Yes, you have 2 minutes.
So now I'm going to the end. This is the last slide. I would like to advertise the Genius program, which is in development at our Heinz Meyer-Leibniz Center. So the partners are at Meyer-Leibniz Center, Forschungszentrum Jülich, Technical University Munich, and Helmholtz-Zentrum Hereon. Started this program to train young neutron scientists through the establishment of a well-structured postdoctoral research program. So this is a co-fund program and has 3 calls to fill up to 15 postdoctoral positions every year. The first call was last January, and already 15 postdoctoral fellows joined us or are joining us by the end of the year. Currently is running the 2nd call by middle of January, and the 3rd call will be next year, November, until January 2024. If there is interest for joining us as postdoctoral researcher at Heinz Meyer-Leibniz Center, you are welcome to apply or contact one of the supervisors which are indicated on the website of this program. And with this, I would like to close to acknowledge contributions of different people to the research studies I presented: Professor Dieter Richter, Luis Fetters, Professor Futoshi Kaneko from Osaka, so Yue Zhao from Takasaki, and my former colleague, postdoctoral colleague Maddalena Schiavone. And I would like to thank you very much for your attention. So it took quite long, but I'm happy it finished.
Okay.
Thank you.
Thank you.